Okay, hi guys. So today we are doing the photoelectric effect. Ooh, there we go. So by the end of this lesson, you should be able to define and explain the photoelectric effect, define and calculate the work function, and then calculate the energy of electrons. So before I start with the slideshow, let me just explain the concept on my whiteboard. Okay, so in order for you to understand the photoelectric effect, I actually have to explain the history behind it first. So you get light, and hopefully in grade 10, you were told that it can act like both a particle and a wave. Okay, so what happened was a few years back, this guy Newton and Hooke had an argument, and Newton said that light was a particle, and Hooke said that light was a wave. And at that stage, everybody kind of thought what Newton thought, that light was this particle, and that is why if you open the window, you can see the little dust particles there. So they kind of went and they said that Hooke's idea was wrong. Then a few years after him, this guy, Max Planck, came onto the scene. And he said that if you had light in a container, then these light particles transmit at a certain frequency. So if it's a blue light, then you see it at a certain frequency. And if it's a red light, you see it at a different frequency. And if it's a green light, you see it at a different frequency. So he said that light had to have frequencies. But not everybody was convinced. Yes, Cal, you're jumping the gun. Not everybody was convinced. So Albert Einstein stepped into this topic in 1905. And he said, well, he agrees with Planck, but he's going to change it a little bit and explain that light could be both a wave and a particle. And what he said was that light has what we call photons. Let me do it in a different color. And these photons are little pockets of energy. They are pockets of energy. And he actually won a Nobel Prize for this, by the way. And then Ernest Rutherford came on after him and kind of built on what he was saying. But what Ernest did was he figured out that if you take atoms and you shoot it into the atom, the gold atoms, a block of gold basically, then your particles would come back. So Ernest came up with the idea that your atoms need to have a nucleus, and around the nucleus, there has to be electrons. This was his idea. But what he couldn't explain was why these electrons didn't move, because somehow they were supposed to with all these experiments. And then came this guy, Bohr, and hopefully you remember him from grade 8, because you had to be able to draw all these models. And what Bohr did is he said that your electrons can be in these energy levels, and that certain electrons stay in certain energy levels. So we learned in grade 8 that you could have 2 electrons in the inner energy level, and then you could have 8, and then you could have another 8 electrons, and so forth and so forth. And what you learned was that these electrons stay in these energy levels. And this was a way for scientists to explain what happens. So what they realized was that these electrons could actually move. So this electron at this energy level could jump to this energy level, or it could jump to that energy level. And this electron on the most outer electron energy level could jump to the inner one, or the one way on the inside. So they realized that these electrons could jump around, but they didn't fully understand why. And so this French guy came along, and he said, his name was de Broglie, that it had to mean that your electrons act like waves. And so what they ended up doing is this experiment where they took this metal, okay, and then they would go, and they were these same type of metal, little metal plates hanging from the metal, and let's say it was in a glass jar. And what they would do is they would shine different lights on it. So this is green light. They would shine different lights on it and see what happens. And what happened was that these little plates on the inside would move away from each other. So they would end up looking like this, repelling each other. And do any of you have an idea why? So before you hit it with light, they would be next to each other, and once you've hit it with light, they moved away. So here they're repelling, and over here they are neutral. Oops. And so what this experiment told us was that somehow this light that shines onto the piece of metal has to do something to force this repulsion to happen. Keegan, if one was positive and the other one was negative, they would actually stick together. Remember, opposites attract and the same repel. So they're both actually negative. So what happened was, when the light shined onto this top bit over here, yes, you're right. When the light shined onto both of them over here, it caused electrons from this big block to move all the way down into these little hanging bits. And when the electrons ended up inside of these little legs, they pushed them away, because now you've got negatively charged metal pieces, and obviously the same type of charge will repel each other. So they ended up repelling. So what this was called was the photoelectron effect. And what we learned was that light has to act like a wave so that it can hit this with enough energy. Okay, it's going to hit it with some form of energy, and that will give enough energy for the system to release an electron. And that energy we defined using this formula. This is the energy of a photon. So remember those pockets of energy I was talking about? This is it. So H is your Planck's constant. Well done, Cal. And F is the frequency of the light that you are using. And very importantly, there's this this formula from grade 10 that F is equal to C over lambda. Okay, and remember that lambda is your wavelength and c is your speed of light, which is always a constant of 3 times 10 to the power of 8 meters per second. Okay, but at the same time, what they also realize is not every light can cause these electrons to move. So what that meant is there is a minimum amount of energy needed. And they ended up calling that the work function. And this is specific for every type of metal. Every type of metal has its own amount, so, or every type of element for that matter. So specific to surface. So some metals will have different values than others. And what it meant was that, let's say all the light from a wavelength of green and lower were able to cause this, then you wouldn't be able to use a wavelength of red, for instance, because they just wouldn't be enough energy. So what we're going to do in this topic is we are going to look at working out this work function or the frequency that is needed to cause these changes. Has everything that I explained so far made sense? Yes, no, maybe. Okay, so I can go back to my slides. Okay, so like I was explaining, the photoelectron effect is just the process whereby an electron is emitted by a substance when light shines onto it. So exactly in that picture, you've got a red wavelength, so a red light, it shines onto that metal, and that is enough energy to cause some of the electrons to become loose and separate from the metal. So then we get to the work function, and like I was explaining to you, it is the amount of energy needed specific to a surface that will knock electrons off of that surface. And the way we indicate it is with a capital W and a small naught next to it as a subscript. And like I was showing, energy of a photon can be calculated using that formula, E is equal to HF, where H is your Planck's constant. And your Planck's constant is actually an amount of 6.63 times, sorry, Carl, there you go. 6.63 times 10 to the negative 34 joules second. So the unit for Planck's constant is joules second. And so what we then can derive from the fact that you have the work function is you have to have a specific frequency. And that frequency is called the cutoff frequency. And it is indicated using a little naught at the bottom of a frequency as well. So it's also a little subscript. So you need to be able to define work function. And we're going to get to an example where you should be able to calculate it. So if they ask you to calculate work function specifically, the formula for that is capital W with a naught equals H, which is Planck's constant, times the cutoff frequency. Keegan is of certain. Honestly, off the top of my head, I cannot think right now, but yes, it should be. You've got a voltaic cell that causes the sunlight to go in and move your electrons into an electric system. But I will double check that for you and tell you tomorrow. Can I go to the next slide? Okay, so then the other thing that happens is sometimes you're going to hit this metal or this surface and you're going to hit it with more energy than what it needs. So more than the work function, okay? And that is defined as the maximum kinetic energy. So that is the excess over and above the binding energy that emits the electron. So that will be the energy that your electron has afterwards. And you can calculate it using that formula. So energy is equal to the work function plus the maximum kinetic energy, or maximum kinetic energy is equal to the energy of your photon minus your work function. And that's just called the photoelectric equation. Okay, then because we're working with electrons and they're also small, and we're talking about really, really, really tiny energy amounts, the other way that we can refer to it instead of joules is actually electron volts. And so electron volts is equal to the charge of an electron times potential difference. And let me just show you how we actually calculate that amount, because then they will make sense. So if I get my whiteboard. Okay, so like I said, energy of E is equal to small q times V. In this case, the charge of an electron is always constant as 1.6 times 10 to the negative 19 coulombs. Oops. And if we times it with 1 volt, you will get 1.6 times negative 19 joules. Okay, and this energy that we are talking about is an electron volt. So 1 electron volt is equal to this amount. So if you then want to know how much 1 joule is equal to how many electron volts, then you can go and divide this by 1.6 times 10 to the negative 19 and divide 1 by 1.6 times 10 to the negative 19. And you will see that 1 joule is equal to 6.25 times 10 to the 18 electron volts. So that's how you convert a joule to an electron volt, or how you convert an electron volt to a joule. And just remember, this can change. So this is always a constant. It is the charge of your electron, and it's always times 10 to the negative 19. And that is how you calculate an electron volt. Okay, so that's all this explains, is that we just use electron volts instead of joules, because sometimes, like I say, we're working with such minute amounts. So if you look at it, if you look at the joules, it's times 10 to the negative 19, but if you look at electron volts, it's times 10 to the positive 18. So it just depends on whether they want it as a big number or a small number. Okay, then the photoelectric effect can be demonstrated on a graph, like over here. And I think I should actually, oops, sorry. And so what this graph demonstrates is your x-axis is your frequency. So that is the frequency with which any light can hit your surface. Your y-axis over here is your kinetic energy. And then you've got your straight line. Which formula? This one? Thank you. Okay. So like I was saying, this is your frequency, and this dotted line over here is your cutoff frequency. So remember, that is the minimum frequency with which your substance can be hit in order for an electron to be knocked out. So if you have anything below this, okay, any frequency below this point will not be able to cause any electron to move off of that surface, but anything above this will. So any frequency above this point will cause your electrons to move off of the surface. Anything below this will cause no electron to move, no matter how intense that light is. So it's very important to know the difference between frequency and intensity. Intensity just means how much light you're showing onto the surface. Frequency is the thing that changes it. And so if you look at this line, then your y-intercept, if you were to extend this line straight into your y-axis, sorry, from your x-axis, you would get your y-intercept, and your y-intercept in this case is actually your work function. It's your W naught. So if I draw it on the whiteboard, whoops. If I have this graph, that should be a straight line, and that as well. This is frequency, this is EK. Let's say my cutoff frequency is over here. So this is my F naught. And that's my straight line. If I take this and I extrapolate this graph back to my y-axis, that point over, oopsie, this point over here would be your W naught. So if you look at your formula, EK max is equal to HF naught minus W naught. Okay, this is your y-intercept. Intercept. This is your x-intercept. And this over here is your what's that, your slope, your gradient. So your Planck's constant in this case is actually your gradient. And then this is obviously your y values. So your work function can be obtained by extrapolating a graph like this using a ruler. And the reason I'm showing you this is we're going to do a past paper tomorrow where you will see they actually ask you to do that. So all you have to understand from this graph, whenever you see it as a graph with Hertz, so joules versus Hertz, and this is your cutoff frequency, then you can extrapolate it to find your work function. Does that make sense? Okay. So here's a question. They ask us, or they tell us that there is an ultraviolet radiation with a wavelength of 250 nanometers is incident on a silver foil with a work function of 6.9 times 10 to the negative 19 joules. What is the maximum energy of the emitted electron? Okay, so always write down what they give you first. So they gave us the work function of, oopsie. Yep, you always have to change it to meters. I was going to say that. So the works function was given to us as 6.9 times 10 to the negative 19 joules. Your wavelength was given to you in 250 nanometers, which is equal to 250 times 10 to the negative 9 meters. And I always have this little way of remembering it. I say month, it's -3, -6, -9, -12. Milli, micro, nano, pico. Which equation? H is your Planck's constant, which is always 3.63 times 10 to the negative 34 joules second. And C is equal to 3 times 10 to the 8 meters per second. I'll quickly show it to you, Talisha. They tell you you've got an ultraviolet radion with a wavelength of 250 nanometers is incident on a silver foil. The work function is 6.9 times 10 to the negative 19 joules. What is the maximum kinetic energy of the emitted electrons? Okay, so we've written down what we have. Now we have to work it out. So we use the formula EK max is equal to E minus WO. Okay, and in this case, the E is equal to H times F, but they give it to us in terms of wavelength, and we know what C is. So this equation changes to H times C over lambda. So I'm just going to substitute that in there. So H is your Planck's constant, which is 6.63 times 10 to the negative 4 joules seconds. C is the speed of light, which is 3 times 10 to the 8 meters per second, divided by your wavelength, which is 250 times 10 to the negative 9 meters, and subtracted by the wave function, which is 6.9 times 10 to the negative 19. Okay, and you can put that into your calculator. Just remember your brackets. You are using a lot of times 10 to the power something. So always bracket everything. And if I put it into my calculator, I get my final answer to be 1.06 times 10 to the negative 19 joules. Please check whether I'm correct. If you're not comfortable putting all of it into your calculator at once, you can just do like the top bit first and just write it out. Thank you, Lisa Kanye. Thank you, Masejo. Okay. So The next part comes down to how do we practically use this? How do we see this? What is the application of it? And so in front of you, you have a picture. And in that picture is what we call a discharge tube. So a discharge tube has metal rods inside of it, okay? And then you'll see there's a gap between the metal rods. And what ends up happening is there's a little spark, or what we call an arc, that goes from the one metal side to the other one. And that arc causes your gas inside of this glass tube to get heated. And when your gas is very, very heated, it causes your electrons of that gas to move from one energy level to the other energy level. And when that happens, we get what you call an emission spectrum, which is a spectrum in which you see these different colored lines because of how the electrons have moved. So, and it looks like this. So what happens is you get this surge of energy. And if these black lines are energy levels, so you've got level 2, 3, 4, 5, and 6 on the picture. And then you've got this energy that's being absorbed. So that's the yellow bit. And it causes your electrons to move. So let's say all of your electrons are sitting on level 2. Then they move up to level 3 and level 4 and level 5 and level 6, for instance. What ends up happening is these electrons move there for like a split second, and then they lose all that energy they've just gained, and they fall back to where they come from, where they're the most comfortable. Okay. And when they fall back into their original energy level, they release that extra energy that they gained. So when they go from level 6 to level 2, they release a certain amount of energy. And when they go from level 5 to level 2, they release a different amount of energy. And same thing from level 4 to level 2, and level 3 to level 2. And because those energy levels are different, it means that the frequency with which the energy is being released differs. And so you see different colors. So as you can see here, when they go from level 6 to level 2, you see violet. But when you go from level 3 to level 2, you see red, which should tell you, if you think about your color, your EMR color spectrum, that this energy level this energy jump has a much higher frequency than this one over here, because your purple always has a higher frequency than the red. So does that make sense? An emission spectrum is when you could drop from a higher energy level to a lower energy level. Does that make sense to everyone? And when you drop from that higher energy level to a lower energy level, energy is released, and we can see it in the form of colors. Okay, and what that looks like is what you have right in front of you. So this is an emission spectrum of hydrogen gas. So if you take hydrogen gas and you put that into that discharge tube that I was showing you, you can get this emission spectrum. So it's only 4 lines, and they are different wavelengths, so they give different colors. And very importantly, every single element has its own emission spectrum. No element's emission spectrum looks the same as another one. And that is how we are able to identify different elements, using emission spectrum. So this is really important in like space, because we obviously can't get samples of things that are billions of light years away. But what we can do is look at these, because remember in space, gases are very hot. You're looking at plasma, stars are plasma, it's very hot gas. We see these colors and we can kind of make assumptions on what type of elements are in there based on this color spectrum that we see. So that's the use of it. Okay, and so what we can do is, when there's a change in these energy levels, we can actually work out the energy of an electron. So the energy that an electron either gained or an electron either lost. And we use this formula. So we say the change in energy of an electron is equal to the final energy, so the last energy level that it had, minus the initial energy that it had. Does that make sense? And we're going to do an example, so don't stress. Does the theory behind it make sense? Okay. So if you look at this picture over here, you will see that on the right-hand side, there's a bunch of joules, and on the left-hand side, it's the energy level. So what they're showing you is you've got your energy level over here, the first energy level, which we call the ground state. So that is normally the state in which your electron is without the atom being excited. So as it is in its normal environment, okay? And then those electrons can move to level 2, or it can move to level 3 and 4 and 5 and 6. And then what happens is it can move back down from 6 to 1, or it can go from 6 to 2, or maybe from 6 to 3. And because these energy jumps, you'll see there's different energy. So each energy level has a different energy amount. So let's say if we look at level 6 over here, it's got 21.3 times 10 to the negative 19 joules. But the energy over here for level 2 is 16.3 times 10 to the negative 19 joules. So to go from 6 to 2, you're going to have a different energy amount released than from 6 to 4, for instance. And so what we get is when there's this big jump in energy from level 6 to level 1, so from the highest one to the ground state, for instance, we get ultraviolet. So we can't see that with our eyes. You can only see it as UV, and we can see it on a spectrometer machine that can pick it up. What we can see is this little bit here in the middle, when it doesn't go to the ground state, but just the state one level above it, then we see the colors that we do. And then when it doesn't go to the ground state or the second energy level from the ground state, but normally anything above it, you see infrared. And that is also a machine that can pick it up. So do you understand what I say with you go from a higher energy level to a lower energy level, and where your ground state is, and that you go, when you go from your high energy levels back to the ground state, it's UV, so ultraviolet transition. When you go from a higher state to the second level just after the ground state, you're at visible light. And over here, when you don't go to those energy levels, but the higher ones, you'll get infrared. Does that make sense? Yes, no, maybe? Okay. So there's an example, but before I show you an example, I quickly want to go back and just show you another picture. So I just want to show you what an emission spectrum looks like. Okay, so you get an emission spectrum, which is the one that I just explained, and then you get an absorption spectrum. So an emission spectrum, if you look at this picture over here, is when you go from the higher energy level to the lower energy level. So you go from level 2 to the ground state. Okay, so higher to lower. Down to lower, that is emission spectrum. You are losing energy, you're giving it away, that excess energy. When you go from a lower energy state to a higher energy state, so lower to higher, it's called an absorption spectrum. So you take energy in, energy is required. So this one consumes energy. And this one over here releases energy. And the difference between them is you will see that they have little stripes at the same place, but they just look different. So for an emission spectrum, you will have a black band, and then you will have colored lines in between it. And those colored lines indicate the frequency because of the color having a specific frequency. And for an absorption spectrum, you will have colored, all the colors of the rainbow, but those lines will be black. And here it's the same thing. So the difference between them is an emission spectrum basically looks like those when you've colored at the bottom and you're scratching it out, the black, and you get the colors. Okay, so emission spectrum, you go from a higher energy level to a lower energy level, and you're releasing that excess energy. Absorption spectrum, you go from a lower energy level to a higher energy level, you're consuming energy. And because those energy jumps are taking the same energy just in opposite ways, you will see the bands at the same place, but they're going to look different. Emission spectrum, black band with colored lines. Absorption spectrum, colored lines with black bands. Make sense? Okay. Okay, so our last example for today. They tell us what color is the light emitted by hydrogen when an electron makes the transition from energy level 5 down to energy levels 2. Use the figure on the previous slide. So they're asking us, we're jumping from 5 to 2, what is the color? So they want us basically to find the frequency. So if you look at this, we're going to go from 5 to 2. So we're going to use this 21.0 times 10 to the minus 19 joules. That is the energy of level 5. And level 2's energy is 16.3 times 10 to the negative 19 joules. So we're going to find the change in energy first. And once we found the change in energy, we can plot it into our normal energy equals frequency times whoops. Sorry, my computer was just freezing for 5 seconds. Can you all see my white screen? So, okay. You all see my whiteboard, right? Just want to double check. Okay, thank you. So your change in energy is you're going from energy level 5 to energy level 2. And we said that energy level 5 had an energy of 21.0 times 10 to the minus 19 minus 16.3 times 10 to the minus 19 joules. Okay, and if you plot that into your calculator, you get a value of 4.7 times 10 to the minus 19 joules. And then we're going to use our, because we want to know what was the color that's being transmitted. So we're going to use E of our photon is equal to H. And in this case, we don't have F, but we have C, and wavelength is what we're looking for. So this, okay, is our wavelength. No, that is our energy. I'm sorry, wavelength is what we're looking for. This is our energy. So if I rearrange my formula, then wavelength is equal to Planck's constant times the speed of light divided by that energy. So 6.63 times 10 to the negative 34 times 3 times 10 to the 8 divided by that amount, which is 4.7 times 10 to the minus 19. And if you plug it into your calculator, you should get 423 times 10 to the negative 9, so 423 nanometers. Does that make sense to everyone? Yeah. Okay, let me just get my slides. So then that means 423 nanometers has to be somewhere between the 410 and the 434. So your color would be probably a type of purple or violet. So your answer would be violet or purple. Okay, so hopefully by the end of this lesson, you are able to define and explain the photoelectric effect. You're able to explain what an emission spectrum is, and you can calculate some of the values. Tomorrow, we will just work through all the past papers. And then by the end of tomorrow, hopefully you guys are pros. See you guys tomorrow.